Hi, everybody. Sorry about the delay there. I had an issue setting up the stream, and then I realized, oh, I don't know if I sent out the announcement that said there was a lecture today. And it turns out I totally didn't. So there were like 0 people in the stream with 2 minutes before class. So hopefully you got the announcement. Apologize for it being late. Maya is here. Maya wants to say hi. Hi. Say hi. Say hi. There you go. Very good. We're going to finish Chapter 5 today. That's our goal. If we can finish Chapter 5, then you are all set for exam number 1. And the review session, that will be tomorrow. So let's get to that. Now, there is quite a bit to do today. And these topics are a little bit difficult, so please make sure that you ask me any questions you might have. For this first section, what we're going to do is we are going to interpret the shape and structure of a molecule in reality. Now, on paper, we've been drawing Lewis structures at whatever angles we want to, and however we can fit it on there, and just making everything like a T, basically, right? So we've been doing stuff like this. So, and I'm not going to actually draw in all of the things, but everything's at right angles, right? Now, are molecules actually like that? Well, if they're flat on paper, we might imagine them to be like that, but it turns out that when we have 3 dimensions available, we get interesting geometries and shapes that occupy 3 dimensions, because we are 3-dimensional creatures too. That must mean that our molecules, to some degree, must also be 3-dimensional, right? Now, it turns out that you can predict the geometry of a molecule very easily based on whatever structure you draw for the Lewis structure. The number of things that are connected to your atoms is going to influence the shape that you draw. If you have 3 other atoms connected, if you have 2 other atoms connected, or 4 other atoms connected, you're going to get different shapes. And there's a very reasonable way to predict why that will happen. And that is this. If atoms and electrons gather around an atom, and they all occupy space themselves because they're electrons, how do they arrange themselves? For instance, let's suppose that I have something like this. Here's my atom. It could be oxygen, it could just be whatever, really. I'm going to have a bond going this way. I'm going to have a double bond going this way. I'm going to have an electron pair going like that. And so what I could say is, all of these things have electrons. So there are electrons in here, because remember, a bond drawn as a line is 2 electrons, right? This right here is 2 electrons. And each of these lines here is 2 electrons. What do electrons do to each other? Electrons always repel. And so that means that those electrons at the top are going to repel each other, these electrons over here are going to repel each other, and these electrons over here are going to repel each other. Now, these are my electrons for my double bond. They're going to stick together, so they won't repel each other, just like these 2 electrons in the pair don't repel each other, or these 2 electrons in the bond don't repel each other. But all of these groups on their own are going to push the other groups away. Hey, this is our space. We 4 electrons live here, and you can't be here. That's fine. This is our space over here. We're the non-bonding pair. Nothing else gets to be in this spot. So what we're going to do is we're going to call each of these entities that I'm going to highlight in yellow. Oops, that's the wrong tool. I want the pen here. Each of these things is called an electron group. An electron group is just a group of electrons around the central atom. And it could either be one bond, it could be a multiple bond, or it could be an electron pair. Each of those counts as one group. Whether it's one bond or two bonds, it doesn't matter. Each of them counts as one group. Okay? All right. So this slide is just saying what that said. I'm trying to find my cursor so I can clear the text on there in case you wanted to read that. So the premise behind this is called VSEPR theory. VSEPR theory is short for valence-shell electron pair repulsion theory. What that means is that, well, let's just go through the terms and we'll explain it. So valence shell, we're using valence electrons, right? These are the electrons on the outside of an atom. Electron pair, all the electrons are in pairs. They're either a non-bonding electron pair, a pair of electrons that form a bond, or multiple pairs that form multiple bonds. And then repulsion. Electrons repel each other, right? So that's what VSEPR means. Now, I know it's pronounced VSEPR, but nobody says that, so we just call it VSEPR. All right. So, again, these are our electron groups that we discussed on the previous slide. Any bonds to other atoms, whether it's a single bond or a double bond or a triple bond or whatever, that particular group of bonds counts as a single group. Or if it's a non-bonding pair of electrons, that counts as a group too. Your task is going to be to draw a Lewis structure and then count the number of electron groups. Okay? So let's do an example where we count some electron groups. I don't know why nothing appeared there, but that's okay. There we go. So what I want you to do is I want you to draw the Lewis structure for these molecules. I'm going to just give you some very simple Lewis structures to do. So first, draw the Lewis structure. Then I want you to count the number of electron groups. Okay? Oops, let me get rid of this over here. So we'll just do that. Okay, so first draw the Lewis structure like we did yesterday. Then count the number of electron groups. Okay? We only care about electron groups around the central atom. Okay, so that's the first atom that's listed. So go ahead and do that. And we'll go over the answers in about 3 minutes or so. All right, one more minute, we'll go over the answers together. While you're finishing up, I'm going to draw the Lewis structures because we should know how to do that by now. All right, so let's count electron groups. So remember, an electron group is any number of bonds connected to some other atom around the central atom, or an electron pair around the central atom. So for this carbon, there's very obviously 4 places that electrons are, and it's these 4. So there are 4 electron groups around the carbon atom. Now with CO2, we only care about what's attached to the central atom. So that means that the only places there are electrons are this double bond and this double bond. So there are 2 electron groups around the central atom. And then finally, we'll apply the same principle over here. So the bonds still count, so these are electron groups. But also, this pair of electrons is an electron group around the central atom. So this also has 4 electron groups around the central atom, which was nitrogen in this case. All right, so hopefully counting the number of electron groups helps you understand what electron groups are, because it's real common to miscount these or count everything that looks like electrons around the entire molecule. You only want the central atom, and any location that has electrons counts as an electron group. So a single bond is 1 electron group. A double bond is also 1 electron group. A triple bond would be 1 electron group, and an electron pair would be 1 electron group. Each of those is 1. All right. So what does this all mean? Well, if you count the number of electron groups, that gives you the shape. And you'll notice that the numbers shown below, 2, 3, and 4, are the numbers of electron groups for all the examples that we've seen so far. 3 being the very first one I showed you where there was like 1 of everything on it. So if I have 2 electron groups, I will arrange them in this orientation. Linear. They will just be 180 degrees apart, opposite of each other. Whatever those groups are, that's where they will be. If I have 3 groups, I arrange them in a triangle. Whatever those groups are, they will be in a triangular pattern around the central atom. And then finally, with 4 groups, whatever those 4 groups are, they will be in a tetrahedral arrangement. Now, this is the weird one. The tetrahedron is strange because we've been drawing squares all this time, or crosses, or T's, or whatever you want to call it. But in reality, it's more of a bunch of 100 or so degree angles. They're not quite right angles, they're a little bit more than that. And so you get this interesting sort of 3-dimensional orientation. Now, what exactly does that look like for our molecules? That's where this program comes in. So it's hard to visualize molecules in your head if you've never done the 3D experiment before, or if you don't have a model. So what we're going to do here is we're going to go to... Hold on. I'm trying to just... I mean, that kind of works. Sorry. That's good enough. Okay. So, window capture, mol view. There we go. So, I'm going to paste this into the chat here. So this program is called MolView, and you can't actually see everything on the top here. I kind of want you to be able to see that. There we go. All right. Let me just click these error messages away because I was just playing around with it. And what MolView does is it lets you draw a Lewis structure on paper. So, for instance, I could draw CH4 like that. And then what it does is I can hit this button right here, and it will try and make it adapt to a 90-degree drawing that would be the most efficient for space that you would draw. But that doesn't actually show the actual geometry. What I then need to do is hit this button right here, 2D to 3D, and it will take this structure, and I've apparently had it hidden off the side here, and it will make a 3D model of it that you can now spin around. And so you could see that this doesn't look like the plus sort of structure that we drew over here. It actually looks like this. So here, there's our tetrahedron. I can rotate it around like this. And so this is what it looks like in 3D. Now, I could make the molecule more complicated if I wanted to. So, for example, this could be another C. Oops, I didn't mean to do that. How do I move this? There we go. And I could just go like this, C, C, C. And then we'll just fill it with H's here. Oops, that's not what I wanted. Sorry, I'm trying to make a molecule that actually exists. There we go. And then I'll neaten it up. Boop. So there's my Lewis structure. Now it's all at right angles. And then I'll do this. And this is what the molecule actually looks like, where all of these carbons are tetrahedrons because they all have 4 electron groups around it. So this carbon right here has 1, 2, 3, 4 electron groups. This one has 1, 2, 3, 4. This one has 1, 2, 3, 4. What shape would that make? You make this little zigzag dog sort of, a little dash-end thing. So you can play around with these molecules however you want to. You could type in the names of molecules. For example, here's caffeine. This is what it looks like. You can then spin it around and see its shape. You're going to have to do this for one of the lab experiments later on. But this really helps you visualize geometry for any molecule that you care to build. So use MolView to check your answer after you've stated what your geometry is, just so you can see what that actually means. Okay, so you could see the trigonal planar arrangements on some of these. So like right here, this carbon in the middle here has one group, this double bond, and another group, this single bond, and another group, this single bond. So there's 3 groups, and so it makes a triangle, but the triangle is flat. The one thing that MolView does not do well is it doesn't show electron pairs. So you don't actually see the electron pair on this nitrogen atom that's right here because it's not shown on this structure. So just be mindful of that. So like if I, oops, that didn't work, but that definitely didn't work. There we go. Yeah, there apparently is no option to draw electron pairs on there. So be mindful of that. You may have to draw the Lewis structure on paper and then put it in here to the best approximation that you are able to. All right, so we'll get rid of that. All right, so those are the 3 geometry configurations that we are going to make our molecules conform to. Our molecules will always be one of these 3 shapes: linear, trigonal planar, or tetrahedral around any given central atom. And you could see in that molecule of caffeine that I showed you, like, you can't see that shape for the overall structure, but for any given atom on the structure, you could definitely see, oh, that looks triangular, or oh, that looks linear, or oh, that looks tetrahedral. All right. And again, up there, the pink atom is the central atom, and then the white atoms are other atoms that are connected, or they could be electron groups. or not electron groups, but or pair of electrons. They are all electron groups regardless of what they are. All right. So now what we're going to do is I want to show you this other simulation first before we talk about this. So I have another simulation that I'll link in the chat for you to play with if you'd like. I do have to load it, so it'll take a second. Oh, that actually went really quickly. Okay. There we go. Boop. All right. There is something at the bottom, and I want you to be able to see it. It looks like you can see everything. Okay, cool. All right. So what this is a simulator where you can construct your own molecule using electron groups. So here's my central atom, and I'm going to add in an electron group. Whoop. Well, there's nothing else there, so it can go wherever it wants to. But the second one that I add is always going to go in 180 degrees away from that. And I can turn on bond angles to show this to you. Now, it doesn't matter what I put in there. I could put a double bond across from it. I could have 2 double bonds. It doesn't matter. Or I could just have 2 electron pairs. They will always go apart from each other 180 degrees to make a linear arrangement. Now, if I put a third thing in here, that's where you get the triangle. And you can see that that's very flat. And if I put a fourth thing in here, whoop, that's where I get the 3D structure. Now, this will let you put more things than 4. For our class, we're only going to go up to 4. But if you accidentally click more and get up to 6 here, just delete them until you get back down to 4. It will let you do whatever you want to, so you can break the octet rule. Because it turns out the octet rule is only a suggestion, not an actual rule. But for our classes, we're going to follow the octet rule. But we're only going to go up to 4. Down here, if I check this box, this will give you the name of the thing that you've constructed for our family. So you can see that our options are either linear, trigonal planar, or tetrahedral. Now, regardless of whether I am building this out of bonds or electron pairs, I will still get the same geometry because all we're doing is comparing this to those families that were on this slide here. All right. So going back to this slide, these terms right here are called electron geometry. So you may be asked, what is the electron geometry? Of a molecule. You may also see it called VSEPR geometry. These two things mean the same. They're the same term. So if you see either of those words, it's asking for what family does your molecule fit into? All right, going back to this diagram here again, or this simulation again, we can actually do an interesting experiment. For instance, we know that electrons and bonds take up space because they are all electrons. They all repel, right? But electrons are much, much smaller than the atoms that they are bonded to. So in reality, my molecule like this, which has 4 electron groups, would actually look kind of like this. You would not see the lone pairs because they're so tiny, but you would still feel their influence because the charge is still there. So what that means is that this molecule, which looks like there are only 2 groups coming out of it, is still bent. In reality, there are 4 groups coming out of it. There are the 4, right? But how does it look? It looks like this. What that means is that its appearance will differ based on the number of electron lone pairs that are there, and we're going to give it a different name. We're not going to call it linear because it's not linear. It's not in a line. Even though there are only 2 groups here, there's actually 4. 2 of them are the electron pairs. So if I consider electron pairs to be invisible because they're so small, we get a new type of geometry, and that's called the molecule geometry or molecular geometry. And so what we're going to do is we're going to go through all of the different possibilities using the simulator. And we're not really going to generate this on the board. We're just going to use the simulator to show you the shapes. But then I will make a giant table of the list of molecules that is on page 130 of your textbook. Okay, so we're going to start first by clearing everything until we're down to just 2. Anything with 2 electron groups is going to be linear, regardless of whether you have an electron pair or not. And the reason for that is because the shape that you generate is just linear. So the electron geometry will always be linear, and the molecule geometry will always be linear. Oops, there we go. If I attach 3 groups to a central atom and all 3 of them are bonds to other atoms, then I just make something that's trigonoplanar, right? So the electron geometry will be trigonoplanar because there are 3 groups, and the molecule geometry will be trigonoplanar because it still looks like that. But if I remove one of these groups and make it an electron pair, then my invisible electron pair makes a different shape. I still have 3 electron groups, so it's trigonoplanar, but now one of those is an electron pair, so I get a different shape. It's bent. And then if I go to 4 electron groups around here, anything with 4 groups is tetrahedral. If all of them are bonds, it still looks tetrahedral. It still looks tetrahedral to me. But if I replace one of them, I get a new shape. This no longer looks tetrahedral. In fact, it looks like a tiny pyramid. So we're going to call that trigonal pyramidal. And then if I remove one of these and put another lone pair on, and then do this, now it looks kind of like the other bent molecule over there. It's just, it has a different angle. So this is how you get bent in chemistry. All right, so now what we're going to do is I'm going to make a table for you that hopefully explains what we saw and also has all the names of the terms on there. So we're going to have first, I misspelled VSEPR. We're going to have for groups with 2, or things with 2 electron groups. Then we'll have things with 3 electron groups. And then finally with 4 electron groups. So our molecule is always going to fall into one of these 3 categories. Then from there, we can determine the molecular or molecule geometry. Based on the number of electron pairs. Well, for 2, it's always just linear. But for 3 and 4, it matters. So if I have 0 electron pairs, then my structure looks the same And the molecular geometry and the VSEPR geometry are the same. But if I have one electron pair, I get a new shape. And then down here for 4 electron groups, I can do the same thing with 0, which still makes a tetrahedron. Or I could have 1 electron pair, which makes that sort of squished pyramid that we had, which we called trigonal pyramidal. Or we can have 2 electron pairs, where we get something that's, oops, that's not very good. Where you get something that's bent. What you're going to do when you are given any molecule is you are going to ask yourself the following questions. So the first question you're going to ask is, which VSEPR geometry does your molecule fall into? In other words, is it 2 electron groups, 3 electron groups, or 4 electron groups? Then you're going to ask, which molecular geometry does it belong to? So, for example, if you had a molecule that had 3 electron groups, this would be your VSEPR geometry right here. And then you would say, okay, how many electron pairs are around the central atom? 0 or 1. And then you would select the correct response that matches your diagram. So a molecule that looked like, say, this down here would be trigonal planar VSEPR geometry and bent molecular geometry. All right. We're going to leave that just here. I made a layer so that we could just draw on it. We're going to do a bunch more examples with this. Oops, I forgot to close the simulator. All right. So what I want you to do now is draw ammonia. Oh, you've already drawn ammonia, actually. So let's just do this example together. So NH3. Because we did this earlier. And we said, okay, how many electron groups are there? Well, I circled these 3 and this electron pair. So there are 4 electron groups. So if we go back to our chart here, 4 electron groups is this right here. So the VSEPR geometry would be tetrahedral. So let's write that down. The VSEPR geometry is tetrahedral. And then the next thing I have to consider is how many electron pairs are around the central atom. Here's one right here, right? So there is 1 electron pair around the central atom. So when I go back over here, I find the one that has 1 electron pair. Here it is. So my molecule that I'm looking at for ammonia is tetrahedral VSEPR geometry, trigonal pyramidal molecular geometry. And so we'll go write that down. And there you go. That's how you assign the geometry to any molecule you want. All right. Now, these examples are just asking for the molecular geometry. I'm often going to want to ask you to do both. You could see that from CO2 that we drew earlier, the molecular geometry should be linear. There are only two groups around it. So now what I want you to do is I want you to draw these Lewis structures to the best of your ability. So draw ozone, SnCl3 with a minus on it. Remember, the minus increases the number of Lewis electrons you have. SeCl2, and then carbonate. So draw these four structures on paper. Use the rules that we talked about yesterday to do Lewis structures. And then count electron groups and then electron pairs. Tell me the VSEPR geometry first, what family it goes into, and then tell me the molecular geometry, which member of that family it is. Okay, I'm going to give you about 5 or 6 minutes to do this. Type your answers in the chat when you've got any, and we'll go over the answers when I get back. See you in a bit. 2 or 3 more minutes and we'll go over the answers together. All right, let's go over the answers here. So first, we'll put this on the screen here. Okay. Now, I don't want to delete this chart yet. I do want to get rid of this that's on top here, though. So what I'm going to do is I'm going to go like that. And let's see here. Where's image? Canvas size. Let's see. I want to make the width 200%. There we go. And then give me just a second. I got to fill this in. Boop. And we're going to draw on that layer here. Okay, cool. All right, so first we're going to draw the Lewis structure of ozone. So let's do that. So for ozone is, each oxygen is 6 electrons, and there are 3 of them. So I should have 18 electrons in my structure. So 2, 4. So the minus 4 is 14. 6, 8, 10, 12, 14. That's all I get, right? Wait, sorry, hold on. That's wrong. 2, 4, 6, 8, 10, 11, 12. So I use 12 here, so I have 2 left. And then I do that. There we go. All right, do I have an octet everywhere? No, I need to make a double bond somewhere, so I'm going to make a double bond here. I could have picked the other side, it doesn't matter. But there's my structure. All right. Now I need to ask myself, where are the electron groups? Well, there's a bond here, non-bonding pair here, and a double bond here. So there are 3 electron groups. So if I have 3 electron groups, what is the VSEPR geometry? Well, if I go back to the chart here, I see that 3 is trigonal planar. So the VSEPR geometry of ozone is trigonal planar. Now, of those 3 groups, 1 is an electron pair. So the molecular geometry is, so if I have 3, 1's an electron pair, then the molecular geometry would be bent. So my structure should look like a bent line. And it kind of does, so that's good. All right, so there's ozone. Let's do SnCl3 here. Is there a minus on that? There is. Okay. So tin gives you 4 electrons. Each chlorine is 7. There are 3 chlorines. And this minus is an additional electron. So that's 26 electrons to work with. There's my tin, Cl, Cl, Cl. So that's 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There's all of my electrons. And then I do the whole thing. It's an ion, so I do that. All right, let's look at the geometry now. So how many groups are around the central atom? There are 4 groups. So if I scroll over, what has 4 groups? That's this one. So the VSEPR geometry is tetrahedral. Of those 4, how many are electron pairs? That's this one. 1 electron pair. So the molecular geometry, scroll over in 4 and 1, and that's this one. So this is trigonal pyramidal. All right. So that's how we do the geometry for those 2. Now I do have to clear this, what I've done here. So you can pause the video if you need to write these down. I'm going to get rid of these right there so I can do the last 2. So for selenium dichloride here, selenium has 6 electrons, 6 valence electrons, I should say. Chlorine has 7 valence electrons, and there are 2 of them. There's the total number of electrons I can work with. Now I can draw the Lewis structure. So that was 4 to do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I have 4 left. 1, 2, 3, 4. How many electron groups are around the central atom? Here's a pair, here's a pair, here's a bond, here's a bond. 4 electron groups. So which one is that? That's this one. VSEPR geometry is tetrahedral. Of those 4 electron groups, how many are electron pairs? Here's one, and here's one. So there are 2 electron pairs. So of those choices, this is the one that matches ours. So the molecular geometry is bent. And then finally, for the last one here, we've got carbonate. Each carbon is 4 electrons. Each oxygen is 6 electrons, and there are 3 of those. And then I've got the additional 2 from that. So I have 24 electrons. I could draw my carbonate like that. That would cost me 6 to make. And then the remaining 18 would go around the outside like this. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I don't have an octet around the carbon in the middle, so I need to move 1 pair. There we go. Let's count the electron groups. 1, 2, 3. All right, if I have 3 electron groups, what's my VSEPR geometry? Here's 3. So my VSEPR geometry is trigonal planar. Of those 3, how many are our electron pairs? Well, none of them are. They're all bonds. So 0 electron pairs. The molecular geometry is therefore the same thing. There you go. All right, that is how we use this chart, how we describe the VSEPR geometry of a molecule, and also the molecular geometry of a molecule. Okay, so use this chart. First, ask what the VSEPR geometry is by counting electron groups. Then ask what is the molecular geometry by counting the number of electron pairs around the central atom, and label that too. There's the homework practice on the screen. We're going to take a short break for 10 minutes. I'm going to put the break timer up here. And we'll get the music back up. And I will see you in just a little bit. we are back. Let's see here. We're going to move on to the next section, which is polarity. Polarity builds off of geometry, so it's very important that we understand how to draw Lewis structures, but also what the shapes of those structures are so that we can understand their polarity. Okay. Before we do that, though, we have to understand a concept called electronegativity. And electronegativity is pretty simple. It's just a number that we're going to assign to every atom based on the following property. In an ionic compound, we transfer electrons from one atom to another. Generally speaking, we transfer them from the metal to the non-metal. And in a covalent compound, we share electrons. The electrons are right between both atoms. Now, is there some sort of in-between state? Can I share my electrons but unevenly? Like, I'll share them, but I get them most of the time. Like, that's technically not sharing in the same sense that it would be for a covalent bond, right? Like, it's kind of, sort of ionic, kind of, sort of covalent. Can we get something like that? And it turns out the answer is sure. Why not? It depends on what atoms you are bonding together. So, for instance, if I put these two atoms on the board here, they're the same atom. They're both chlorine. Which chlorine wants the electrons in the bond more? And you might say, well, that's silly. They're both chlorine. They want it equally, right? Because electrons are pulled towards the nucleus. Whose nucleus will pull harder? Well, they're the same. So, the result is the same. There's no difference here. So the electron density would be distributed evenly throughout. And we could say that it's exactly in the middle. The electrons will be, on average, right between these two chlorines. Oops. And so that's what the slide is saying. What about this situation, though? Who is going to pull the electrons closer to its nucleus? Well, hydrogen's really tiny, and chlorine is much bigger, so the electrons are going to move more in this direction. They're still shared somewhat, but chlorine keeps them most of the time. He keeps it closer to him, so it's easier for him to access. It's kind of like if you had toys with like a younger sibling that you shared with them, but you kept the toys in your room. They're technically closer to you. You have more access to them. But your sibling, he or she could come to your room and borrow them if they wanted to. That's not technically equal sharing, but it's still sharing. And that's what's happening here with H and Cl. Chlorine's going to pull the electrons real close to its nucleus because it's more able to do that than hydrogen is. So on average, the electrons in this bond will be closer to chlorine than hydrogen. Now, there are all sorts of reasons why this happens. We're using the size of the nucleus as one factor, but there are other reasons too, such as the size of the atom. Where are the electrons relative to the nucleus? Are there other electrons in the way, etc.? And we don't really cover those topics in this class because that's quantum mechanics, and just hearing those two words together probably scares you. And it should. Quantum mechanics is ridiculous. So we're going to quantify this instead with just giving all these elements a number that we have already ascribed on a table somewhere. And so this property is called electronegativity. The electronegativity of an atom is just how strong does an atom pull electrons towards itself through bonds. Hey, there are people in the chat. Hello. I was like, am I giving this lecture by myself today? There are people here. I saw that there were 4 students this whole time, so thank you for watching. I appreciate it. Now, how do we assign electronegativity? We're going to give it a number between 0 and 4. 4 is the most electronegative, and 0 is the least, although no atom actually has 0. And that chart you can see right here. Now, this is in your textbook. I just don't remember what page it's on. And it changes between editions. I do have the 5th edition here. It should be around like page 140 or so. Let me flip through. Ah! A little too far for that. Not 140. It's page... Where the hell is it? There it is. Page 123 in my edition of the text. But the one on the screen is much more complete, so I think that this one is probably more useful. So you might want to like screen cap this slide and then save it to a file so that you have it handy if you have to reference it. There's also tons of these online, so you can just refer to any electronegativity chart. They're all going to be more or less the same. Now, where are the most electronegative elements? I was just giving you a second to look at the table real quick here. The most electronegative elements are in the top right corner of the periodic table. The least electronegative elements are in the bottom left corner of the periodic table. So in general, electronegativity increases as you go to the right and up. So fluorine is the most electronegative. Francium is the least. You'll notice that hydrogen is included right here for some reason, even though it should be way over on the far left. I think it's put there just because its electronegativity is close to boron. Now, why are these numbers what they are? They have to do with how big the atoms are. So as you go left to right, atoms get more protons, and protons pull electrons to the nucleus better. But as you go down the periodic table, your electrons start to get stacked farther and farther away from the nucleus, and so it's harder to reach those. So fluorine just happens to be the best balance of lots of protons, and the electrons are all still relatively close by. All right. So what we're going to do is we're going to assign every atom a number in a bond, and then we're going to check to see what the difference between the atoms is, and we're going to categorize the bond based on what we see. This is just a summary of which elements give away their electrons versus which elements take electrons and their electronegativity. So we already knew that, so we'll talk about that later. All right. So if we look at two atoms in a bond, and we see that the difference between electronegativities is about 0.4 or less. Oh, I should actually highlight less then. Okay. Actually, I don't really like how that is written because it's not quite right. Okay, so I'm gonna go like this. So we're gonna go 0.4 or less. Because I want to include 0.4. There's a particular bond that I'm thinking of that we categorize as nonpolar. All right. So if we look at the difference in electronegativity and we get this number, 0.4 or less, we're going to call it nonpolar. Nonpolar means that the electrons are virtually in between the atoms at the center point. So that's going to change this number right here. So that means if electronegativity falls between 0.5 and 2, the electrons are going to be shifted towards the more electronegative atom. We're going to call that polar covalent. So if I have a difference in electronegativity of more than 0.4, so 0.5 or higher, all the way up to 2, then the electrons are shifted towards the electronegative element. They're still shared, but they're just shifted. And then finally, if the difference is just greater than 2, then what ends up happening is that the electrons are pushed so far over towards one atom that they're essentially just taken. For example, if you pair lithium and fluorine together, the difference is so large that the lithium essentially has no claim to the electrons anymore. They are now just given to fluorine. Now, there is one exception to all of this, and the exception is that if you ever have a metal involved, the bonding is ionic. For our purposes. This is a bit of a generalization, but I'm trying to stay consistent with your text here, so I will just comment that if there is a metal involved in your bond, the intent is that it is ionic. Now, as you can tell, we've already done some Lewis structures with things like tin in them. Tin is not super electronegative, but it's also not very electropositive. Like, it's kind of in the middle. And so you can actually make covalent bonds with it. But for our purposes, we're just going to treat stuff as either being ionic, because there's a metal, or covalent because it has a low difference in electronegativity with nonmetals involved. All right. So let's do some examples here. So I have hydrogen here. So here's hydrogen's electronegativity. Here's fluorine's electronegativity. I'm going to calculate the difference. I'm going to call that delta En. And so that's 4.0 minus 2.1. And I get 1.9. So I would call the bond in HF polar covalent. Now, how do I represent that on paper? There are two systems that we use to do this. The first is to draw symbols right over the numbers I drew, because that's how this works, right? Okay. The first is to use these symbols. Now, if charge is represented by these symbols up here, this is charge. We're going to devise a symbology for partial charge. We're going to put this delta plus and delta minus. What this means is that it's sort of charged. Not a whole charge, so it's not a whole electron being moved, but the effect that we feel is as if we have moved part of an electron. And in a sense, we have, because if the electrons are not shared evenly, the electrons are spending more time on one side of the molecule than the other, their charge is going to be felt more on that other side. So these terms that we have here, this delta plus and delta minus right here, these indicate a partial charge. Think of it as just like plus 0.5 or plus 0.2 or something like that. The other way that you can draw this is you could draw an arrow. And so what we'll do is we're going to draw an arrow pointed at the more electronegative side. So this is the more electronegative side, and this is the less electronegative side. We have this little plus symbol here to indicate, oh, that's the more positive side. And we point the arrow at the more negative side. That's going to be useful to us in just a second when we determine whether molecules are polar or not. All right. So do I have some examples here? No, I don't have any examples for this. So what I'm going to do is I'm going to go to the sample preview. Oh man, we put so much work into this and I'm about to delete it, so. Goodbye, table. All right, so what I want you to do, I'm going to put a bunch of bonds on the screen here. We don't really need this right here, but. So I'm going to put some bonds here. And what I want you to do is I want you to determine whether they are polar, nonpolar, or ionic using the electronegativity numbers. And in fact, what I'm going to do, we're going to go like this. Oh, that went behind the chat. I don't want that. Hold on just a second. Let me move that up so it's over the chat. And then I'll toggle this back to that. There we go. Which, unfortunately, it's kind of small, but there you go. All right, so using the electronegativity chart here, I want you to categorize each bond that I've drawn on the screen as one of those categories: nonpolar covalent, polar covalent, or ionic. And we'll go over the answers in just a second. All right, 1 or 2 more minutes to do this, and we'll go over the answers. All right, so let's look at these electronegativities off this table here. So looks like carbon is 2.5 and nitrogen is 3.0. So the difference here should be an N, and I can't write today. Is 0.5, so this bond would be polar covalent. Only just slightly, though. And because it's polar covalent, we could indicate that by going delta plus, delta minus, or drawing the arrow in this direction. For this one over here, CH, the difference here is 0.4. We're going to call that nonpolar covalent. If it's nonpolar, we don't draw any symbols. It's not polar, right? Oh, you can't see that because the this is in the way. There we go. Here's OH. Oops, no, that's not right. 3.5. When I do the subtraction, I get this. So this is also polar covalent. And we would point towards the more electronegative atom, or put delta minus on the more electronegative atom's side. You don't have to do both notations. I'm just doing both, just to show you them. And then I can't quite read that number. What is that number for cesium? 0.8. Not that it really matters, because cesium is a metal. So we just call this ionic. And what we would do is do something like this. And then we would get rid of this right here, because ionic bonds are not represented by lines. They are represented by just writing the charges there. Only covalent bonds are represented by lines. Whether they're polar or not, you still leave the line there, though. All right. So now that we know how to calculate electronegativity differences for bonds, we don't really need to do the calculations anymore. All we really need to do is worry about these arrows. We're going to point the arrows at the more electronegative things, because most pairs are going to be electronegative if a metal's not involved. And by electronegative, what I mean is most pairs are going to be polar. So what we're going to do is we're going to consider the polarity of each bond using arrow notation. We can do the numbers, and as long as we get 0.4 as long as we get 0.5 or higher, we're going to draw an arrow. Then what we're going to do is we're going to compare all of these arrows together. And that's actually a little bit difficult to do, but we're going to do the best that we can. What we're going to do is we're going to say, okay, the electrons are going to travel along these arrows away from the center of the nucleus. But sometimes the arrows will pull against each other, so the electrons will just go back and forth towards the center. If all the arrows cancel each other out and all of our electrons just land back where they started, in the middle, we're going to call our molecule nonpolar. But if the electrons get moved somewhere else and they don't get pulled back, then that's where they stay overall. And we're going to call the molecule polar. The property of polarity in a molecule is going to be really relevant to us in Unit 7 when we talk about intermolecular forces, because the polarity of molecules is how water sticks to other things and why water dissolves things like salt. And it's very, very crucial for setting up the conditions for life to flourish. So it's really important to understand polarity. Let's look at some examples here. So here's carbon dioxide. I've drawn the molecule CO2, and I have determined that the electronegativity of this is big enough that it warrants an arrow. So I have drawn the two arrows. I have a CO on the right and a CO on the left. And you'll notice that those arrows are pulling in opposite directions. So in other words, my electrons starting here are going to be pulled in this direction, but also in this direction, right? What is the overall result when these electrons are pulled in both directions? And the answer is, well, we're going to compare the arrows. Here's my first arrow, and here's my second arrow. So where did my arrows start here? So here's what we're going to do. We're going to add the arrows together. If you've ever seen vector notation in physics before, this is what we're doing. So when you add arrows together, you add them, you start where the previous one ended. So here's my first arrow. I started here at this point. I ended here. So my next arrow is going to start at the end point. And you'll notice that I did this. I started here and I went to that, and then I came straight back. In other words, what my electron density did on my molecule was it was pulled in this direction, and then it was just pulled right back, and now it's here again. It's right in the center of the molecule. So is this molecule polar? The answer is no. My electrons were pulled right back to the center, so they're not pulled in one direction overall. Let's look at another example. So we've got SO3 here. I've got my electron density, it's being pulled up, and it's being pulled down and to the right, and also down and to the left. But if I look at all of those in sequence, how do all of those forces affect each other? Now, I've removed the plus parts of these arrows just because it makes it harder to animate. But I can pick any arrow I want to, and then add them, and to start. And what do you notice about where my electrons go? They sort of do this thing. Woot doot doot. They went back to where they started, so this is nonpolar. SO3 is nonpolar. But what about water? Let's do the same thing for water. What do you notice happens here? This is what happened with my water. The electron density sort of just ended up over here, as opposed to being in the center of the molecule. So it's been moved across the molecule. There is an overall polarity. This is where I started. This is where I ended. So that's like saying my electron density was moved in this direction across the molecule. We don't need this bend in there. It was just moved like this. So on this side of the molecule, I would have delta minus, and on this side of the molecule, I would have delta plus. And we would conclude water is polar. So this is the means by which you determine whether something is polar or nonpolar. You're going to look at all the polarities of all the bonds. And then you're going to compare them to each other and sort of follow the arrows. They show you where the electrons go. Now, there are some cases where it's very difficult to do this sort of analysis. And the reason for that is because we end up going in 3D. So if you have stuff that's tetrahedral, it becomes very difficult to draw these structures. And you can actually mislead yourself. So for example, is ammonia polar? So what I'm going to do is I'm going to try and draw ammonia to the best of my ability in 3D. So ammonia has a trigonal pyramidal molecular structure. And hopefully you can see that when I draw all of the polarity arrows here, so N is more electronegative than H, so these are all going to point at N. If I do the same sort of analysis, I'm going to get something that looks sort of like this, right? So there's the first arrow, there's the second arrow, and there's the third arrow. Here's where I started, there's where I ended. So overall, my electrons went in this direction. So I would write that the electrons are on the top part of the molecule most of the time, gives us a delta minus. Down here, there are less electrons overall. So we would conclude that NH3 is polar. Now, in more advanced classes, I would ask you to conclude which direction the polarity goes, so which side of the molecule is negative and which side of the molecule is positive. For our purposes in Chem 121, I'm just going to ask you polar, yes or no. So draw the molecule to the best of your ability, see where the electrons go, and if it looks like they go straight back to where they started, tag no as on your option. Is it polar? No, it's not. If they end up somewhere off in the weeds, so not where they started, because all the arrows seem to be going away from each other, or not away from each other, but away in the same direction from the center, then the molecule will be polar. All right. We have enough time to do these examples, so I'm going to have you do these 4 examples here. First, draw the Lewis structure, then draw the polarity arrows and see where things shift. Be very careful about tetrahedrons. So PCl3 has a tetrahedral VSEPR geometry, so does CH3Cl. The other 2 should be a little more straightforward. Draw the structure the best you can, and we'll go over the answers in just a little bit. One more minute, we'll go over the answers here. All right, let's go over the answers real quick. Oops, I gotta clear this because I don't have space. There we go. Oh, and that moved over here. All right, so first we're going to draw the Lewis structure. We're going to, again, draw it as accurately as we can. So hopefully for PCl3, you drew something that looked like this, because its VSEPR geometry is tetrahedral. And then we'll draw all of our electronegativity arrows. So chlorine is more electronegative than phosphorus. So all these arrows are going to point in this direction. And so you should be able to tell here that my arrows are all sort of pointing in the down direction, and there's nothing that's really pointing up to undo that, right? You could draw these all sort of connected to each other if you want to, and the end result that you get is something like that. So that means that the bottom side of the molecule is delta minus, and the top side is delta plus. So we would conclude that this is polar. Now, CS2, we have sort of the same issue that CO2 has. Oops, that's supposed to be an S. In that C and S would point in opposite directions, although they have the same electronegativity to begin with. So if they're both 2.5, then you don't really draw any arrow because they're nonpolar. And so the end result you get anyway is nonpolar. And even if you drew arrows, you should probably be able to see that they point directly away from each other, and so you just end up right back where you started. How about C2Cl2? This molecule is like C2H2 that we did yesterday, and the result that you should get should look like this. Now you have a bunch of bonds to consider, and it's like, well, what do I do? Well, C and C there's nothing to draw between these two. They're nonpolar. But chlorine is more polar than carbon, so I would do that. And then you can see that if I stack these two arrows on top of each other, I'll just go over to the left and then come right back, right? So this is nonpolar as well. And then finally, CH3Cl. I'm going to just put the Cl on top, though it doesn't matter. We said earlier that CH bonds were nonpolar, so there's only one bond in here that actually ends up being polar, and that's that. So if this is the only polarity arrow that's present, then this is the result. If it can't cancel out with anything else, it must be polar. All right. Polarity is pretty tricky. So make sure that you do as many of the examples in the homework practice that you can. There's a lot of them. So there's like 30 problems here in the homework exercises to just draw structures, learn and explore polarity, and then put it all together to look at a molecule. Remember, all we care about is polar versus nonpolar on our molecules. All right. We are out of time for today. Unfortunately, there is one more section that I do want to cover. So what's going to happen is that tomorrow, before we do the review session, I'm going to cover naming covalent compounds. This last section at the start of the review section tomorrow. And then once we have covered this, the remainder of the class will be review. And so you can bring whatever topics you want me to go over. I'll be happy to cover them. You can cover anything on the worksheets, anything from the textbook. I would prefer not to do lab stuff because the exam is mostly on lecture stuff and very, very little of it comes from the lab, if any, actually. So I will still answer lab questions if nobody has any other questions, but the emphasis on tomorrow's review session is going to be lecture content and any questions that you might have. If you're watching this video after I have posted it, and you have questions you want to ask at the review session but can't make the review session, what you can do is send me an email, and I will try and get those questions into the review session and answer them to the best of my ability. You can send me an email or post in Discord, and I will make sure that those get in there. All right, that's all I got. We'll see you tomorrow for the review session. Make sure you get quiz number 4 in tonight. Get lab number 2 finished. It's due tomorrow. Have a good night.